Thank you. Yeah. So, cool. Here we go. Yeah, so I'll be talking about Mosaic, which allows us to leverage many different types of reflectors for around corner radar, automotive radar, despite my preference for trains. Oops, wrong button. There we go. So first off, why do we need beyond line of sight sensing? So the first talk already mentioned this briefly, but basically I think everyone who's ever driven a car knows that what you can't see while driving is especially dangerous. So in fact, some people have previously done some studies on natural driving data using instrumented vehicles with normal people driving around the road, and they found that around 30% of crashes at intersections have to do with this problem of blocked lines of sight. And in fact, in these particular cases, the blocked lines of sight were so serious that even if we did have a theoretically perfect advanced driver assistance system using conventional line of sight sensors, we still would not be able to prevent that crash. And it's also dangerous for pedestrians. So around 18% of vehicles colliding into pedestrians are also associated with these blocked sight lines. So what can we do about this? We have a bunch of existing technologies. So people have tried out all sorts of different things in non-line of sight configurations. So a LiDAR can be used in the non-line of sight configuration. You can do sound-based sensing. You can do thermal imaging. You can use visible light imaging and use all of these in non-line of sight configurations in some manner or another. The kind of two key problems that we see with all of these, though, is that either you need a very controlled environment for this to work, so lots of the pictures up here look very controlled, or, and in many cases we see both these problems, that lots of the sensors that you need to do this sort of non-line of sight sensing are expensive or exotic or otherwise not generally available. The other solution that we mentioned previously is some evolution of DSRC or CV2X, where we either share sensor data or we share the positions of vehicles. This is obviously a very valuable approach, but it requires widespread deployment of some sort of technology. So maybe you want to share sensor data between vehicles. Maybe you want to deploy sensors on your infrastructure so that you don't need sensors on your vehicles. In all of these cases, you need some sort of widespread deployment. You need lots of cooperation between vehicles. So what if we want to start solving these problems right now instead of waiting for widespread deployment of these sorts of solutions? Well, non-line of sight radar fits lots of the requirements here. So we can actually do it with commodity radars that are already fitted into vehicles. So people have actually already tried this a number of times. And they found that we can find a hidden target object to avoid a collision by basically using the wall like a mirror. So any reflection of a moving object that you see behind that wall, we can assume is reflected off the wall. We just flip the image across the wall and we find the actual object location. So this works quite well in their evaluations, but in looking through these papers, I noticed something very interesting, which is that the particular locations of the wall that we use as this relay reflector tend to be very common. There's a very specific locations that all these papers seem to have these reflectors in. Which leads us to our problem. Non-line of sight radar with planar reflectors actually is not very good. Basically, it depends very heavily on where we place those reflectors. So if we don't have a planar reflector directly in front of our vehicle, we have these triangular blind spots in our intersection. The red regions that we see here. And in fact, we ran some simulations using kind of standard ray tracing techniques. And even in this pretty ideal scenario where we have buildings right up near the road, very rich multipath environment, the walls will only give us about 60% of the region near the intersection. And in an application where we really need a lot better reliability than that, just using walls alone will not reliably enable us to do non-line of sight radar sensing. So my immediate thought was, what other reflectors can we use other than just the walls? So we have poles for street lights. Those are all metal. Maybe those would make good reflectors. We have trees. We have fences. We have the corners of other vehicles in the environment. But will these actually work well as reflectors? So we find that there's some significant challenges if we want to use these sorts of reflectors. So the first and most obvious is limited detection range. So especially if you're using something like a tree, if you've ever tried to check how much multipath signal you get off a tree, it's not very much. Basically, all these reflectors are a lot smaller than these large walls. They're a lot less, they're more irregular, so the signal scatters. We also have this problem of angular resolution. So again, these reflecting objects are very irregular, so they don't act like a nice, clean mirror like the walls did in the previous tests. And finally, we have the problem of environment variability. So even if we try all the different reflectors we could possibly find in an environment, that we aren't necessarily going to be able to achieve non-line of sensing in every case just using these reflectors, because there's a lot of variability within the different intersection environments we encounter. So first we're going to look at this limited detection range problem. And before we try to solve it, let's try to quantify it. So what we've done here is we had a pedestrian kind of moving in a region that was hidden from the radar. We set up a reflector in front of the radar, and we asked the question, what's the maximum total range to that pedestrian that we can sense? So the total range is the distance from the radar to the reflector plus the distance from the reflector to the pedestrian. A concrete wall, it's very variable performance based on what particular wall you're trying to use, so anywhere from 13 to 33 meters. If we try to use a traffic light pole, around 12 to 13 meters. Tree trunk shockingly works, but only at very short ranges, so less than 5 meters. And then using the different parts of a sedan in that picture, we got around 8 to 16 meters of range. So the question is, will this work? Is this enough range? So for reference, the road right outside of our hotel from curb to curb, so excluding the sidewalk, is about 7 meters wide. Lots of these reflectors are only giving us 13 or less meters of range. So we need to somehow extract some more range from our existing sensing system. So obviously part of the problem is that our reflectors are kind of weak, but we can, another very interesting problem that we find is that non-line of sight sensing with radar is different in a rather fundamental way than trying to do line of sight sensing. And that is that our angle of arrival and our angle of departure can actually be different. So when you're trying to just sense a line of sight object, the path from the radar to the person is the same as the path from the person back to the radar. But if we have multiple reflectors, the paths can actually be different. So line of sight signal processing doesn't work in this case. But what we can do is we actually create a custom detection algorithm that finds these asymmetric transmit and receive paths using path reciprocity. And what we find is that we can, on average, in this particular scenario, we're trying to check for oncoming traffic. We do some tests in the real world. We find that we can achieve an average of 3.4 decibels of improvement and increasing the detection range by about 20%. Our second issue is our angular resolution. So remember, our reflector is really irregular, so we don't know exactly where the reflection is coming from. Maybe it's somewhere along this ellipse that's centered at the reflector. How can we fix this? Well, we can use multiple reflections from multiple reflectors. So by combining multiple range measurements from these different reflectors, we can compensate for our lack of angular resolution. And by using this sort of multipath, we can reduce the localization ambiguity by up to 83% compared with kind of a naive approach where we don't use these multiple paths. And in fact, in some real tests with some lampposts, we find that we can achieve about a half-meter mean squared error in our localization of a person, basically without any sort of angular information from our reflectors. Our third problem is our environment variability. And for this, we approach this by asking the question of, can we slightly modify how we design our roadside region so that we can more consistently achieve this non-line of sight sensing? And basically, because we are enabling the use of these much smaller and irregular reflectors, we can use things like a small sign or a lamppost pole to basically fix coverage problems. So basically, our flat objects, even a small flat object will give us very good non-line of sight sensing range, but its field of view is bad. A cylinder will give us very poor range, but it has a very wide field of view. So basically our algorithm combines these two types of objects and fills our coverage gaps. So now we want to ask the question of whether this will work in the real world. So we pick a number of real intersections with real cars going through, and we take some radar measurements. So in this place, for example, we don't have, at the top of that T, we don't have any wall or any other reflector available. We just have some, we have walls on the two sides of the road at the bottom, and we have some very irregular reflectors. Here, we have walls at some irregular angles. We have bollards, which are just metal cylinders around the corner. And we still have an occlusion that's blocking our line of sight. And finally, we have a scenario kind of like what you would see in a suburban highway. So we have some earth berms are blocking our view of, there's a building on the corner, but we can't use that. So all of our non-line of sight reflector options are these traffic signal poles. So can we achieve good sensing abilities using just those traffic signal poles to see around these corners that are blocked by foliage, for example? So the first question we need to figure out is what sort of performance do we actually need? So in general, our ability to prevent a crash with a human driver is dependent on the time before the crash that we can detect an oncoming collision. So based on some prior literature in the automotive safety world, we find that we need at least 1.5 seconds to get the best results in at least avoiding a collision entirely. So what sort of range do we get? We find that we can get this optimal advanced notice when a car is traveling up to 25 miles per hour. For a truck or a bus, we can actually achieve this sensing even on higher speed roads because they have a much larger radar cross-section. So when they're traveling up to 45 miles per hour. And we also want to know how much are using these irregular and other small reflectors actually helping us. So obviously, in the scenario where we only have traffic light poles, 100% of our reflections are coming from these quasi-omnidirectional reflectors. But even in these scenarios where we have lots of walls nearby that would normally give us some pretty good multipath, we find that less than 31% of our non-line of sight detections are coming from these large walls. In fact, even the small objects, these quasi-omnidirectional reflectors, will give us the vast majority of our non-line of sight detection ability. So in conclusion, what we found is by adapting our detection algorithms to this non-line of sight paradigm, we can achieve a 20% improvement in our sensing range. We can achieve this very low MSE of about 0.5 meter by using path diversity in conjunction with these omnidirectional reflectors. By automating our radar-aware environment design, we can adapt our environment to enable non-line of sight sensing in places where there's not a lot of multipath available. And overall, our techniques give us around a 3 times increase in our probability of being able to detect this oncoming collision. So with cars, we can achieve this reliably, even with just traffic light poles on roads with speeds of up to 25 miles per hour. With larger vehicles, we can do it at even higher speeds. So now I'll take any questions.